Okay, continuing where we left off from our last lecture, talking about the Border Gateway Protocol and both the internal and external Border Gateway protocols. I want to talk a little bit about the information that's sent to different routers using BGP. So to start off, we need to understand that each autonomous system has a unique identifier that's assigned to it, basically an ID number. And this ID number is used to identify the autonomous system within the information that gets sent between the routers. So when a router advertises a prefix across a Border Gateway Protocol session, it includes with the prefix a number of Border Gateway Protocol attributes, and that would include information on the different autonomous systems that you might have to traverse to get to that address prefix. So the prefix plus its attributes is called a route. So two of the attributes that we're going to talk about are AS path, or autonomous system path, and next hop. So AS path contains information about the autonomous systems through which the advertisement for the prefix has passed. So when a prefix is passed into an autonomous system, the autonomous system adds its autonomous system number, its unique ID, to that AS path. So suppose, for example, we had a prefix for the 138.16.64 network, and that's advertised from AS2 to AS1. If AS1 then advertises the prefix to AS3, the AS path would be AS2, AS1. So let's take a look at this and compare that to our little drawing over here. Hopefully this isn't too hard for you to see. You're kind of split screening here. So if you have AS2 and AS1, and suppose out here AS2 is aware of this prefix, it's advertised to AS1, then AS1 decides to advertise it to AS3, the AS path would be AS2 and then AS1. So it would basically provide the information not only to AS3 to know you have to go through AS1, but through AS2 as well. So next hop is the router interface that begins the AS path. So imagine gateway router 3A and AS3 advertises a route to gateway router 1C in AS1 using external BGP. The route will include the advertised prefix and an AS path to the prefix. The advertisement will also include the next hop, which is the IP address of the router 3A interface that leads to 1C. So let's go back to our split screen here again and kind of walk through that if we can. So let's stretch this out. Maybe this might make this, well, I guess not making it that much easier to see, but it's a little larger. Okay, so let's walk through that again. So you have gateway router 3A, and it's within AS3, and it's going to advertise a route to 1C, which is the boundary router for AS1, using the exterior Border Gateway Protocol. The route's going to include the advertised prefix that's trying to advertise and an AS path to that prefix. It will also include next hop, which is the IP address of the router 3A that leads to 1C. So 1C, if it knows wants to get to some network out here, not only is it going to know all the autonomous systems it has to go through, but it's also going to know that the next path, the next hop is going to be router 3A, and it can advertise that to all of its internal routers. And this provides more information as far as how to get out to that advertised prefix. So, path attributes and BGP routes. So as we mentioned before, the advertised prefix includes the Border Gateway Protocol attributes. And we just talked about them right here. So this kind of summarizes what we were just talking about. So AS path contains the autonomous systems through which the prefix advertisement is passed. And the next hop indicates the specific internal AS router to next hop autonomous systems, which we just saw in the previous example. Now, the gateway router, and this is where we talk a little bit about policy. We're going to see some examples of why sometimes this isn't just mathematical formulas, but sometimes from a system management point of view, we're going to set up some routes via policy. So for example, when a gateway router receives route advertisement, it uses it predefined by some sort of network manager import policy to accept or decline route advertisements. So it may say never route through a particular autonomous system. And like I said, this might be because, say you're an ISP and you want your routes for your customers to go a certain way because that's how you're going to make the most money. Or you don't want to, you're trying to control certain data aspects of your network. So you'll set up some policy-based routing that may have nothing to do with performance, but really some other business variables. Okay, for routes, Border Gateway Protocol uses both the external and internal, or exterior and interior, Border Gateway Protocol to distribute routes to all the routers within autonomous systems. The router may learn about more than one route to a destination autonomous system, and it learns them based on, and it selects the routes rather, based on routes assigned a local preference value as on their attributes, either set by the router or kind of a policy thing, or learned by another router in the autonomous system. And this is a policy decision left up to the network administrator. Routes with the highest local preference value are selected. Routes may learn about more than one route to the destination autonomous system, and they may select based on this criteria. One being, for remaining routes, the shortest autonomous system path is selected, and it uses a distance vector algorithm for path determination, where distance metrics is the number of autonomous system hops. Then finally, for the remaining routes, so of course we started over here with policy-based routing. Then we're going to go by the shortest path. For the remaining routes that have the same local preference and the same autonomous system path length, okay, so they don't have any advantages in those senses, that sense, we route to the closest next hop router, for which the cost is the least cost path, determined by the intra-autonomous system is the smallest. So now we're talking about inside our internal autonomous system where the best next hop router is to get out to the external network. And this assumes that our internal autonomous system is somewhat complicated. because if not, this would be the same answer all the time. So we talked about basically some of the contents of the Border Gateway protocol messages. Let's talk a little bit about kind of mechanisms of Border Gateway protocol messages. First of all, the messages are exchanged between the peers over TCP connection. We start off by opening up the connection to the peer, and we authenticate the sender. That's very important from a network security point of view, that we have the ability to, authenticate the network data that we're going to receive. So we have an update message once we have set up our connection that allows us to either advertise new paths or get rid of invalid paths. We have a keep alive message, which keeps the connection alive in the absence of updates. And keep alive is also used to acknowledge open requests. And we have a notification message that reports an errors in previous message. And this is also used to close the connection. So since we have some overhead in opening up a connection, we try to basically keep the connection open for the most part. So that's why we do this. We have this keep alive command, keep alive message. So let's talk a little bit about how an entry gets inside the forwarding table. Basically, there are 3 steps that have to occur. So let's take a look at this drawing first of all. And you basically, in this particular drawing, we have our router in question, and the router is running some routing algorithms like we've just been talking about, and it's using these routing algorithms to populate its local forwarding table. And basically it gets an entry that has a prefix of 164.16.64, and it's determined because of its due to the routing algorithms that data for that prefix needs to be routed out output port 3. So what has to happen for this information to be placed in this forwarding table? Well, at a very simplistic level, the router becomes aware of the prefix. So obviously it has to get some sort of message like we just talked about. And then it has to determine the output port for the prefix. So in these 2 cases, it's using the data it's going to be receiving using BGP, and it's going to use policy and other information and basically calculated information to determine the output port and then find the correct output port, and then finally it's going to enter the prefix/port information into the forwarding table. So let's take a look at these a little more closely. So the first step, the router receives a Border Gateway Protocol message that contains some routes. The route is a prefix, as we mentioned, a prefix plus attributes. So, for example, and the attributes are the AS path, the autonomous system path, and the next hop plus the prefix itself. So here's an example. So imagine a Border Gateway Protocol message is sent to router 1C, the boundary router in autonomous system AS1, and it is this information, this route that we just talked about, which is basically the route prefix, the subnet prefix 164.16.64, the path, which is AS3, and then from AS3 it's going to go to AS131, and the next hop, which is going to be this IP address, which I'm going to assume is the IP address of 3A. Now the router may receive multiple routes for the same prefix. So it could be getting data from Autonomous System 2 and Autonomous System 3 about that same prefix. So it has to select one of the routes. So in this case, it received a route from Autonomous System 2 and one from Autonomous System 3 to the same subnet. So basically, because this route has the shortest Autonomous System path, 2 hops versus 3, it's going to select this one as the best route. So it's going to route things out to Autonomous System 2 rather than Autonomous System 3. What if there's a tie? We're going to come back to that. To find the best intra route to a border gateway protocol, we use the selected routes next hop attribute. So the route's next hop attribute, as we've mentioned previously, is the IP address of the router interface that begins the next path. So the border gateway protocol record has an AS path of AS2 and AS17 and a next hop of 111.99.86.55, which is the boundary router in AS2. So the routers within this autonomous system will use the shortest path, or in this case, 1C, is going to use OSPF to find the shortest path from 1C to 111.99.86.55. Now, obviously, it has multiple paths it can go through. 1D, go through 1A, but it's going to use OSPF to determine that 1B is the fastest way to get there. And if any of these other routers have that information, they'd have to make that same determination. For the router to identify the ports for a route, it identifies the port along the OSPF shortest path, and then it adds a prefix port entry into its forwarding table. So following on from the previous example, 1C knows that the fastest way to get to 2A, the next hop for that path, is through port 4. So it adds port 4 to the prefix port entry inside its forwarding table. So let's summarize what we just discussed. So we start off, first the router becomes aware of a prefix, and this is where our border gateway protocol route advertisements from other routers. Then it determines the router output port for the prefix. To do that, it first uses the border gateway protocol to route the selection to the best inter-autonomous system route. So basically we could have more than one route. In fact, we very often do have more than one route to get to a prefix, and border gateway protocol route selection is going to help us figure out the best one. Then within our own internal network, we need to find the best intra-autonomous system route that leads us to the best inter-autonomous system route, which we just did, looked at in the previous example. Then we've got to finally identify which router port is the best to get to that best route. And then finally, once this information has been determined, we can enter the prefix inside our forwarding table. So the next thing we're going to talk about is border gateway protocol routing policy. Now I know all of us tend to think of things in technical terms, and we tend to like to think that every decision made by a computer or a router is going to be based on some mathematical formula or some very specific scientific or mathematical or electrical or computational decision. But keep in mind that basically networks are used by businesses, and businesses make decisions based on other factors than technical. So as a result, Border Gateway Protocol supports routing policies where you make decisions based on, allows you to make decisions on routing based on things other than technical information. So take a look at the diagram, and basically each of these squares, these kind of odd looking, maybe kidney shaped little cartoons here, are supposed to represent a provider network, and the little circles are supposed to represent customers. So these can be small businesses, or maybe that's probably the best way to look at it. It's probably like a small business type thing, and this is your provider. So this could be Cox and Comcast and Verizon. Doesn't really matter. So you have the three providers, and you have your three customers, and you have a customer that basically is dual homed, it's attached to two networks, and that does happen sometimes. Sometimes businesses will actually subscribe to two different providers just to kind of give them more reliability. So if one provider is offline, they can use a second provider, or they can load balance between the two. So let's say X decides it does not want to route from B to C via X. So X is attached to both networks, but it does not want the traffic from B and C, even though it's very capable of doing so, to come through it. So it will not advertise any routes to B, a route to C, even though it knows how to get there. Here is another example.